Today I'd like to go over the nuclear stability graph. Here's what it looks like, and it compares the number of neutrons along the y-axis versus the number of protons, the z number, along the x-axis. Now, for elements that have atomic number less than 20, they have about the same number of protons and neutrons inside the nucleus. So it's pretty much a 1-to-1 ratio, and you can see that they follow along this straight line right here. This has a slope of 1 because there's 1 neutron for every 1 proton. Okay, so it's the n equals z line, if you want to call it that. But for elements which have an atomic number of greater than 20, you can see that the stable isotopes veer off from that straight line, and they follow this dark curve here, ending at atomic number 83. That's the biggest stable element in existence. Okay, that's bismuth, atomic number 83. Any element with an atomic number greater than 83, and they're unstable. So anything out here is unstable. Anything along this dark line right here is stable, any isotope. Okay, so if we looked, we see, okay, this right here, this, if something has atomic number of 50, which would be like 10, and if it has a little over 60 neutrons, that would be stable. However, if 10 had way more than 60 neutrons, that'd bring it out into this range. That'd be in more of an unstable area, So we can use this graph to help us determine whether an isotope is going to be stable or unstable. Okay. We can also use this graph to help us determine whether a particular radioactive isotope would undergo alpha decay or a particular kind of beta decay, whether beta minus decay or beta plus decay, or if there's maybe electron capture or something like that going on. Okay, so that's kind of cool, actually, Let's take a look at something like polonium-84. Okay, polonium-84 has 84 protons, so that would be here. That's just a little bit beyond bismuth, so that's it could be an unstable ground, And let's see what it would have. Polonium, I should say 214. It has 84 protons, but then if we subtract, say, 214 minus 84, that'll give us the number of neutrons. So if we think about a polonium nucleus, it would have 84 protons in it, and 84 from 214 is 130 neutrons. So that's for the polonium-214 isotope. Let's see where that falls. So here's 84 right here. We move up vertically, and then we go over to 130, which would be right here. I'll move over to that. I'll try to stay straight. And so that's beyond this band of stability, isn't it? So that means that polonium is unstable. It's going to be radioactive, okay, since it falls to the right of this bold stability band. Okay, so can you predict what polonium would tend to do? Okay, well, it would tend to radioactively decay so that at least the products of its decay, its daughter nuclei, would be more stable than it. Okay, so how could it do that? Well, it could give up a couple of protons if it could reduce the number of protons, so if we go to the left, that's reducing the number of protons, and reduce the number of neutrons, then at least its daughter nuclei would be close to this stability band, huh? So that's what polonium tends to do. It tends to undergo alpha decay so that, and alpha decay is where it would release a helium nucleus. Helium nucleus doesn't have it's two orbital electrons, so it has a +2 charge. But anyway, that's alpha decay. So I could just write that out. So here we have polonium 214, and it would tend to undergo alpha decay so that it would reduce its number of protons and neutrons. Okay, it would reduce the number of protons by 2, and it reduced the number of neutrons by 2 from 4 is 2 also. So we'd end up with lead 210. And lead has atomic number of 82. So lead 210, and then out of that would fly a helium nucleus, or an alpha particle, it's called. Okay, so this would be the daughter nucleus of the parent right here, polonium. So polonium would radioactively decay into a daughter nucleus called lead-210, while also giving off a helium nucleus, or in other words, an alpha particle. Okay, notice that lead-210 with the atomic number of 82, and if we subtract, let's say 210 minus 82, that gives us 128 for the number of neutrons. So 128, and 82. That gets us closer, at least. It doesn't necessarily bring us right on to that bold stability curve, but it gets us closer. And so that's the idea. Eventually, if we have further nuclear decay, then eventually the daughter nuclei would end up being along this band of stability here. Okay? Let's take another example. Let's look at cesium-137. Okay, cesium-137. So I'll just write that here. Cesium-137 has an atomic number of 55. So I'll go to 55 and draw a vertical upward. And then let's see how many. I'll have to use a calculator. I'm so tired right now. 137 minus 55, 82 neutrons. So the cesium nucleus would contain 55 protons and 82 neutrons. So let's go up to 82 here. That's 90. So this would be 82. And we'll just move over. And we can see that cesium would end up being right here, cesium-137. And that's a little bit high, cesium-137, away from that stability band. So what would cesium tend to do? Well, it would tend to reduce, it would like to reduce the number of neutrons, so that at least its daughter nuclei would be close, if not on, that stability graph. Okay? And that's exactly what cesium does tend to do. When it does radioactively decay, it converts to a daughter nucleus called barium-137. Okay? With atomic number of 56. Okay, so it actually goes over more like this, a little bit. Okay, and in the process, it gives off an electron flying at a very fast rate. This electron here is a beta minus particle. It's beta decay right there. Okay, that's this electron that flies off is a beta particle, beta minus. Okay, and So what's happening in here is that one of these neutrons, let's say there's a neutron in cesium-137, it's converting to a proton and an electron. So this is what's happening inside that cesium-137. Okay, so instead of having an extra neutron there, it reduces its number of neutrons by 1 and increases the number of protons. So really, the process is resulting in a daughter nucleus that's over into this area right here. Okay, so that's how that works. So I gave you an example of where we have alpha decay and another one where we have beta decay. So if we're to the right of your stability graph, the parent nuclei would tend to radioactively decay until its daughter nuclei would be farther and farther over to the left and down on this graph, closer to that stability band. If on the other hand we have something that's just above the band up here, it would tend to radioactively decay so that its daughter nuclei would be lower down that way, and that means that we'd have to reduce the number of neutrons only, or we could reduce the number of neutrons and increase the number of protons and go this way like that. That'll get daughter nuclei closer to that band of stability. So if we have elements in this area, we would tend to have beta decay, beta minus decay occurring to bring the daughter nuclei closer to stability. If we have radioactive elements over in this area, well, the radioactive decay that would tend to occur would be alpha decay, which would decrease the number of protons and neutrons. So it would step by step get us to closer and closer. On the other hand, what if we had something like this, where we have oxygen 15? Okay, let's find oxygen 15. Well, there's 8 for the atomic number of oxygen. 8 from 15 gives us 7, so we have 8 protons and 7 neutrons in that particular isotope of oxygen. So I'll go up to 7. There's 10. There's 7. We end up right here below the band of stability. So this is oxygen 15 right here. So in order for it to decay, it's going to tend to decay so that its daughter nuclei tend to be stable, so it's going to have to move upward in this direction. Well, that would mean that we have to increase the number of neutrons, huh? Okay, well, this is kind of the opposite of beta minus decay. So in this case, since oxygen is below the band of stability and it wants to make daughter nuclei that have more neutrons, the type of decay it's going to that will occur is beta positive decay. It's going to make a nitrogen 15 isotope. It's going to result in that, and it's going to result in a positively charged electron called a positron, which will fly off at a very fast speed. And this particle here is also known as a beta positive particle, or a positron. So here's beta positive decay. What ends up happening is that one of the protons, if this is a proton here, inside oxygen 15, it converts to a neutron and the antiparticle of an electron, which is a positron, a positively charged electron. So this is what's happening inside the oxygen 15 nucleus. We're increasing the number of neutrons by 1, and that means that we go up vertically in the graph from where oxygen 15 is to where nitrogen 15 is, and that gets us back onto the nice stable band of Okay? So that's how that works. Now, just to finish off here, let's look at what's called a decay series, and I'll just use this one for uranium-238, and then I'll flip back and forth. Notice this is the series of radioactively decays that occur from the isotope uranium-238 all the way down to lead-206. Okay? So remember, radioactive isotopes are unstable. They tend to radioactively decay so that they can result in daughter nuclei that are more stable and that will tend to conform along this curve of stability here. Okay? So we could actually, if we had to, we could figure out what uranium-238 would tend to form next as a daughter nucleus. And it turns out that it would undergo alpha decay, go over and down, and form the daughter nucleus thorium-234. Thorium-234, however, would be above the curve here. If we just look at this curve, thorium-234 would be above the curve, and so in order for it to become more stable, it would produce daughter nuclei that would be down lower, and that means that it would result in beta decay. And sure enough, thorium undergoes beta decay to produce protactinium. Okay? Similar things happen. Eventually, after a couple more steps, we get uranium-234. That ends up being over to the right of the curve, then we above and to the right, and so we end up with another alpha decay to bring us back down. Eventually, though, after many, many decays and many, many generations of daughter nuclei being formed, we end up with lead-206. Okay? So this is an example of a decay series. This one happening to be for uranium-238. Okay, in general, okay, the bigger the atom, the more neutrons are needed to keep it stable, but eventually, when the atoms get really big, none of them are stable anymore. Beyond bismuth, or with atomic number 83, they're not stable. So they will tend to break down radioactively in various ways, either by alpha decay, beta minus decay, beta plus decay, or some other processes that I didn't go over. Okay? Okay, thank you everybody.